Hello and welcome to this lecture number 1 of week 11 of the course on control engineering. We'll do a little more analysis of state space methods, the formulations before we go into solving actual control problems. Before that, we'll do a little bit of mathematical preliminaries. Some of them might be familiar with an earlier course on linear algebra, but we will quickly revisit some of the concepts and why they are useful to us. So we start off with defining a linear combination of vectors. So any combination of vectors by means of vector addition and scalar multiplications forms a linear combinations of vectors. So if I have a vector A, if I have a vector A and a vector B, I can simply write 2A plus 3B as some. So a linear combination would be some number times the first vector plus some number times the second vector would give me a resultant vector. So this is what we classify as a linear combination. Okay, so in general, if I have k vectors, let me call those k vectors as v1 till vn. A linear combination would be in such a way that each of these vectors is multiplied by a scalar, right? So v1 is multiplied by a scalar v1, v2 is multiplied by a scalar k2, and so on until vn is multiplied by by a scalar or a number kn. So this is called the linear combination, right? So where all these k's are just belong to some real numbers. Okay, this could also be minus 2a minus 3b also, right? So it's nothing to do with the numbers just being positive. Okay, now second is when are these vectors linearly independent of each other? So whenever we look at our maybe three-dimensional coordinate system, we look at the x-axis, we look at the y-axis and the z-axis. In some vector calculus courses, we represent the unit vectors as I, j, k with a hat, and represent any vector in 3 dimensions as say some 3i plus 4j plus 2k and so on. Which means I can write the vector as a linear combination of the unit vectors in the x, y and z direction. Okay, so I start with a vector space. So at the moment, just think of it as collection of all vectors. So a set of vectors are called linearly independent if there exist scalars such that the linear combination, such that whenever the linear combination of the vectors is 0, which means the numbers in the numbers k1 till kn are also 0. To speak in words, the linear combination of vectors results in a 0 vector if and only if all the scalar multipliers are 0. So let me take two vectors, say 1, 0, 0, 1. These are two vectors in R2. Let me say I multiply this by k1, I multiply this by a scalar k2 and ask myself when are these 0? I can just write down, expand this to say, so the first vector will just be k1 0, second vector will be 0, k2 equal to 0, right? And then so when we add vectors, the components add individually, right? So this will mean that k1, k2 both equate to 0, which means k1 and k2 both are 0. And we know that if I look at R2, say just the two-dimensional plane, 1, 0 will be the unit vector along the x-axis, 1, 0 will be 0, 1 will be the unit vector along the y-axis, and any vector in R2, say 6, 4, if I write this as a vector in R2, this can be written as 6 times 1, 0 plus 4 times 0, 1. Okay, so What happens if they are not linearly independent? They will be linearly dependent. For example, if I take a vector 1, 0, then again I take a vector 1, say 0, 1, and say another vector, say 2, 3. Okay, so are these linearly independent? We'll just check if that is true or not. We'll just write on the journal. Okay, so I'm looking at vectors of the form 1, 0, 0, 1, and what was the number there? 2, 3. Okay, 2 and 3. So when I say I want to find numbers k1 times the vector 1, k2 times the vector 2, k3 times the vector 3 equal to 0. So the first one, 2 will give me, so I'll have a k1 plus 2, k3 is 0, and then again I'll have a k2 plus 3 times k3 equal to 0. So if I, so does this mean, so I'm not solving an equation for k1, k2 and k3. So does it mean that this is equal to 0 if and only if k1, k2, k3 are 0? We'll ask this question. But if I say let k1 equal to say minus 2, k2 equal to minus 3, k3 equal to 1, then what happens? So the first term will give me a minus 2, 0. Second term will give me a 0, minus 3. Third term will give me 2, 3. So if I add this up, this will become 0. This has become 0 even though k1, k2, k3 are non-zero. All of these are non-zero. The other case, when I took linearly independent 1, 0, 0, 1, so this k1 times this plus k2 times this was 0, implied k1 equal to k2 equal to 0. Okay, we can try several other vectors of the form also, right? This 1, 1, minus 1, 1, this is also linearly independent. Okay, so these are like two examples. So what is, if all the k's are 0, then it is called linearly independent. But then if there are scalars which are non-zero and still the linear combination goes to 0, then the vectors are linearly dependent. Okay, now we know, we start with a matrix A. Let A be a n cross n matrix. Sometimes I will also denote this as A n cross n. Okay, so what happens here is, okay, what is the definition of an eigenvector? We all know that we can write this, that A minus lambda I, we do the determinant of this and check for this to 0, solve for lambda, and then we get the eigenvalues. And similarly, eigenvectors A minus lambda I times x equal to 0 will give me the eigenvectors. Okay, so geometrically what it means is that now here x is a vector, okay, and when I multiply it with A, so suppose x is a vector, I multiply it with A, I get some scalar times x, which means the resultant can be something just like here, right? It can be here, it can also be here, it can be a shorter one also. So the vector only scales in magnitude and does not change the direction when a linear, when multiplied by A. So when I say a linear transformation is applied to me, it just say multiply by a matrix A. Okay, so there are eigenvalues and eigenvectors associated with every square matrix, and multiple eigenvectors can be associated with a single eigenvalue, and so on. Okay, how do we compute this, right? So first, eigenvalues are given by the roots of this equation. So if I simply look at this A equal to 7, 3, 3 minus 1. Okay, so I'll write down what is A minus lambda in. So in here will be the 2 cross 2 identity matrix. In general, it's n cross n, but here I am just talking of just it will have, it's an identity matrix of the same dimension of A. So I have A, which is 7, 3, 3 minus 1 minus lambda I. So this will be 1, 0, 0, 1. This is a 2 cross 2 identity matrix. So I have a lambda here, a lambda here. So this will result in equation. So in a matrix of the form 7 minus lambda, I have a 3. Then I'll have a 3. I have a minus 1 minus lambda. And if I look at the determinant of this, I am now looking at determinant is 7 minus lambda times minus 1 minus lambda minus 9 equal to 0. So whatever this results in. So this is a quadratic equation. Solve for lambda to get the eigenvalues. Of course, I will not go into the computations of this. This is very straightforward for it. Okay, so this equation is referred to as the characteristic equation with n roots, where n is the size of the matrix. And the roots of the characteristic equation, they may be distinct, they may be repeated, right? It may just be that eigenvalues are 3, 6 and 9. They can also be 2, 2, 4, 4, right? They can be distinct, they may be repeated. And the corresponding eigenvectors, therefore, are the non-zero solutions of a system of equation of this form. A minus lambda I times x equal to 0. Of course, the solution, I am not interested in the solution when x equal to 0. I am interested in the solutions when x is not equal to 0. What is important, of course, we will not do the details of all of this, is that eigenvectors corresponding to distinct eigenvalues are linearly independent, which means suppose I have eigenvectors, eigenvalues lambda 1 and lambda 2, corresponding eigenvectors are E1 and E2. If they are distinct, then E1 and E2 are linearly independent. Okay. Okay. Now, again, I am just kind of going through this rather quickly, but we'll just see, just try to learn how much of only the parts that we need, and leave the details for a little later. Okay. So now when I say that I have to each eigenvalue, I am associating an eigenvector. Okay. So now if lambda 1, lambda 2, lambda 3 are distinct, then my E1, E2, E3 are linearly independent. Now, if I have three linearly independent vectors, I will say that the dimension of eigenspace of A, which is the vectors E1, E2 and E3, will be 3. So these are the number of linearly independent eigenvectors associated with the matrix A, which has 3 distinct eigenvalues. Okay, now look at them specific. So this is kind of easy. Okay, so the interesting thing happens when I have repeated eigenvalues. Okay. Which means say lambda 1. So my eigenvalues are say lambda 1, lambda 1, lambda 1. Say the same eigenvalues occurs thrice. Okay. In that case, what happens to the eigenvectors? Okay, let me do a simple or very simple example and check what happens. Okay, take a matrix A, which is, well, pretty simple. A is the identity, therefore the eigenvalues are 1, 1. Okay, what happens to, okay, if I look at A minus lambda I times x equal to 0, A minus lambda I will just be the 0 matrix, 0, 0, 0, 0, x equal to 0. Okay, so x here is a vector in R2, so let me write this as x1, x2. Okay, so what are the x which satisfy the, say, equation star? Okay, so let me just check. Will 1, 1 satisfy? Answer is yes. Will 2, 0 satisfy? Answer is yes. Will minus 6 and 8 satisfy? Answer is yes. So any vector in R2 is an eigenvector of 1, 0, 0, 1. And then I'll ask myself how many linearly independent vectors exist in R2? The answer is 2. So I can find 2. So given A is 1, 0, 0, 1 with eigenvalue 1, 1, these are repeated and not distinct, we get 2 independent eigenvectors. Okay, I'll do one more example and now say A is 1, 1, 0, 1. A question: what are the eigenvalues of A? Well, the answer, I'll skip the computation. This is not important to us. Eigenvalues will still be 1, 1, 1. Then what are the eigenvectors? Okay, so I'll just do A minus lambda I times x equal to 0. A is 1, 1, 0, 1 minus lambda I is lambda is equal to 1. So I'll have 1, 0, 0, 1 times, say, the set of all vectors x1, x2 equal to 0. This will lead to 0, 1, 0, 0, x1 times x2 equal to 0. Okay, so this implies, so what is the solution of this? X2 equal to 0 and x1 can be anything, which means that 1, 0, say minus 6, 0, or in general any vector of the form a constant here and a 0 is an eigenvector of A. Okay, what after this? Can I find anything more? No. So all the eigenvectors are of the form C, 0. And then, even though these are infinitely many number of vectors C0, but how many are independent? There will be only one, because this vector is linearly independent on this vector, like minus 6 times the first vector will give me the second vector. So I can find only one. So again, given A is 1, 1, 0, 1 with eigenvalues 1, 1, I can find only one linearly independent eigenvector. So what is happening here? So two things. We start in this example, the eigenvalue lambda equal to 1 occurs 2 times, and there are 2 independent eigenvectors. Okay, here similar lambda equal to 1 occurs 2 times, but it has only one independent eigenvector. Okay, so this number here, this 2 we will call as the algebraic multiplicity, the number of times a single eigenvalue occurs, and this will be called the geometric multiplicity. That the number of linearly independent eigenvectors associated with that repeated eigenvalue. So here algebraic multiplicity is 2, geometric multiplicity is also 2. Then I go to the next one. Here the algebraic multiplicity is 2 and geometric multiplicity is 1. So that is what this slide talks of. So given the multiplicity of an eigenvalue lambda, in general it can be 2, 4, 7, whatever. So the geometric multiplicity is the dimension of eigenspace, that is the number of linearly independent vectors associated with an eigenvalue. Algebraic multiplicity is the number of times that particular lambda appears. Geometric and algebraic multiplicity can be different. We saw for the same lambda equal to 1 comma 1, I had a matrix which gave me a geometric multiplicity of 2, and another matrix again with eigenvalues 1 comma 1 gave me geometric multiplicity of only 1. In general, geometric multiplicity will be less than or equal to the algebraic multiplicity. You cannot have lambda equal to 1 comma 1 and find 3 linearly independent eigenvectors. It will never happen. Just that's what linear algebra doesn't allow that to happen. And sum of algebraic multiplicity of all eigenvalues is n. So suppose I have a matrix which is say 3 cross 3. It will have say eigenvalues lambda equal to 1 comma 1 comma 3. So this is algebraic multiplicity 2, this is algebraic multiplicity 1. The total will add up to the dimension of the matrix. Okay, and then if, so this is important, if for every eigenvalue of A, whenever the geometric multiplicity is equal to algebraic multiplicity, we say that the matrix is diagonalizable. Don't worry if this is a new term, we will get familiar with this very soon. Okay, so that's what we did an example. Now the same thing, geometric multiplicity is 1 for the same example, algebraic multiplicity is 2. We can try doing it for this example and check. So because the algebraic multiplicity is not equal to geometric multiplicity, this matrix is not diagonalizable. Again, the problem comes only because the lambda equals 1 occurs 2 times. But if it's a matrix with lambda equal to 4 comma 6, that is always diagonalizable, because the algebraic multiplicity of 4 is 1, algebraic multiplicity of 6 is 1. We will always find one eigenvector associated to each of these, and they will always be linearly independent. Okay, so what are the properties of diagonal matrix? So I will quickly read this. This may not be very relevant, very directly applicable, but some of these ideas will be useful to visualize what is happening. So rank of a diagonal matrix is equal to its non-zero diagonal elements. The diagonal elements of a diagonal matrix are its eigenvalues. So I will just say till P1 till, should I write P1? I'll just write P1 till Pn. Now something nice seems to be happening, because we can relate eigenvalues to stability. So if I can diagonalize a matrix, what sits on the diagonal are just the eigenvalues. I just look at those signs of eigenvalues and I can maybe infer stability from this. Okay, and product of two diagonal matrices is also another diagonal matrix. Nth power of a diagonal matrix is also a diagonal matrix. We will see why this is also very useful to us. Okay, and inverse will just be, so if I have P1 till Pn, the inverse of this will be simply 1 over P1 till 1 over Pn. This is also like fairly straightforward. Okay, so what do I mean by diagonalization now? If a square matrix is similar, again we are using these words, but slowly get used to this terminology. If a square matrix is similar to a diagonal matrix, then it is said to be diagonalizable. Okay, so I'll just quickly read the definition of similar, even though we'll analyze this a little later in detail. So two matrices A and AZ are said to be similar if there exists a non-singular matrix P inverse. Non-singular, which means determinant of P is not equal to 0, also means that the matrix is invertible. Okay, so two matrices are so here A and AZ are similar. Okay, so we'll come back to where we started off. So which means now this looks a little familiar, right? So I can also write this as A equal to E D E inverse, right? So A and D are supposed to be are now similar in this sense. Okay, so square matrix A is similar to a diagonal matrix, then it is said to be diagonalizable. So let's say I have eigenvalues of A as lambda 1 till lambda n with eigenvalues E1 till En, then the eigenvectors. So if E1 till En are the eigenvectors, then the square matrix is diagonalizable. Okay, let me quickly tell what this means. So I have a matrix A. Let's say this matrix is just 2 cross 2 matrix, or A 2 cross 2. Okay, so suppose I have two distinct eigenvalues and each of them will give me a eigenvector E1 and E2, which are related in such a way that A, so what's the formula that relates eigenvalues and eigenvectors? Ax equal to lambda x. So A E1 is lambda 1 E1, A E2 is lambda 2 E2. I can write this also as A E1 E2. So you see, these are just E1 and E2 are just like vectors, right? Okay. So if I just stack them together, this E1 comma E2 will now be a 2 cross 2 matrix. Okay. So this now will be, I can write this as E1 E2 and a matrix now which will have on its diagonal, a diagonal matrix which will have entry corresponding to the eigenvalues of the matrix. So now I have A times E is E times T, okay, or I can write this as A is E D E inverse, or D is E inverse A E, and this implies that both A and D are similar matrices. Okay, so that is what this diagonalization business is all about, right? Okay, and then okay, let me just do an example first, right? So I have a matrix of the form 2, 6, a 0 and a 1, and I have eigenvalues. I'll just skip these computations. Eigenvector corresponding to eigenvalue minus 1 is 2, minus 2 and 1, and similarly eigenvector corresponding to lambda equal to 2 is 1 and 0. So what I do is I just go back to this formula. So I construct the E matrix. E matrix is now the stack of both the eigenvectors, okay, and when I do E inverse, okay, this is my E, I can compute the inverse, and the inverse will always exist because these two vectors are linearly independent. If I do a E inverse A, multiply it with the E again, what I get is a matrix which just has diagonal of, which just has eigenvalues of A on its diagonal. So this matrix A is diagonalized to D, and what is it doing that? This one. So give me a matrix A, multiply it on the right with the set of eigenvectors, or a matrix composing the eigenvectors. On the left, multiply it with the inverse of E, which is a set of all eigenvectors, and you will get a nice diagonal matrix on the right hand side. As an exercise, you can try doing this. Again, this is very straightforward. Okay, so we saw examples where lambda was equal to 1 comma 1 and I got only one independent eigenvector. Okay, so matrices such matrices will not be diagonalizable, where the algebraic multiplicity is not equal to geometric multiplicity. They are called defective matrices because they are not diagonalizable. Okay, so for example, here for lambda equal to 3 comma 3, algebraic multiplicity is 2, geometric multiplicity is 1 in the same steps as we did with earlier. Okay. So, defective matrices of size n cross n have less than n linearly independent eigenvectors, and therefore, these matrices are not diagonalizable. Then what do we do for these things? So, can I, is there some hope? Maybe can I get something which is closer to a diagonal matrix, if not exactly a diagonal? So, what do we do now is we have the concept of a generalized eigenvector, right? Generalized eigenvector is, I don't just look at A minus lambda I times x equal to 0, but I just have a p on top, where p is a positive integer. Okay. So, again, as this is some terminology from linear algebra. If you don't understand, you can just ignore this sentence. And the value of p corresponding to lambda can be at most equal to the algebraic multiplicity. So, in the case where eigenvalues were 1 comma 1, p can at most be 2. If this is equal to 3, 3 and 3, p can at most be 3. Okay. And eigenvectors are generalized eigenvectors with p equal to 1. Now, we will see if these generalized vectors help us in constructing something close to a diagonal for a matrices which are defective, in which means that the algebraic multiplicity and geometric multiplicity are not equal to each other. Okay. So, what we just do is something like this, right. So, the way is I find x1, one eigenvector I can always find. How do I find the second one? I just do A minus lambda I x2 equal to x1. I'll just do a very simple example where we started off with that was this one, right. So, here algebraic multiplicity was 1, geometric multiplicity. So, what was the any eigenvector was of the form c comma 0. So, let's take it up from here. So, A was 1 1 0 1, lambda was 1 comma 1, E1 was 1 comma 0, but I am unable to find E2 such that A minus lambda I E2 equal to 0, E2 which is linearly independent of E1, E2 linearly independent of E1 for which this holds. Okay, so what I do is I just look at A minus lambda I E2 equal to E1. That's what this says, right? Okay, I'm just changing notations here. Here x's are the eigenvectors. So what is A minus lambda I here? A minus lambda I, we computed it to be 0 1 0 0. Okay, this is nice. 0 1 0 0, E2, I'll just call this as say E21, E22, some numbers here. What was E1? E1 was of the form 1 0 or any C comma 0. So, what do I get from here is E22 equal to 1 and E11 can be anything. So, my vector now is of the form sorry, this should be E22 should be equal to 1. E22 is 1. So, any vector of the form 0 1 is now a generalized eigenvector. Okay. So, the natural eigenvector is 1 0. The one which comes from solving the generalized eigenvector equation is 0 1. How does a diagonal look like? We started off by writing this down to say that A was E, D, E inverse, where D has a very nice diagonal structure with eigenvector sitting on the diagonal. Let us now check what happens with this one, right. So, I have A lambda is lambda x1. So, I am just looking at a matrix with eigenvalues lambda lambda. algebraic multiplicity of 2 and geometric multiplicity of 1, which means the matrices are defective. And then I look for solutions to for this one, A minus lambda I E2 equal to E1. Okay, let me just call this E1. Then I have A times lambda A minus lambda I A minus lambda I. So this is the same as this. Sorry, okay, I just made a so this should be A times E1 is lambda times E1. Second, so this will change now to the expression for the generalized eigenvector. This is E2, or A times E2 is now E1 plus lambda I E2. So just stack both them up. A E1 E2 will be again E1 E2. The first will be A E1 is lambda E1. Second will be A E2 is 1 times E1 and lambda times E2. Okay, now this is my A, this is my E, this is E, and this is a nice structure. It still has eigenvalues lambda lambda on the diagonal, but has some 1 sitting here, which is okay, right? So I just have lambda 1, 0, lambda, and this will now be called as J, the Jordan form. Okay, now what will happen if this were lambda 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 with algebraic multiplicity equal to 3, geometric multiplicity equal to 1? I will add to this one extra expression, which will now look like A E3 is so okay, I'll just write one step before. So A minus lambda I E3 equal to E2, or A E3 is E2 plus lambda E3, and the matrix J will now have the form lambda 1 0 0 lambda 1 0 0 lambda. Okay, this is one case. Other case could happen is that algebraic multiplicity equal to 3, geometric multiplicity equal to 2, in which case the third equation becomes, because I can find 2 independent eigenvectors, third equation will become A times E3 is lambda E3, in which case J becomes lambda 1 0 0 lambda 0 0 0 lambda. Okay, again this is just stacking these expressions into some. So this is called the Jordan form. Okay, and that's what this rest of the so to solve this, again lambda equal to 1 1, the basis was 1 0 and 0 1. We can also try doing the same for 3 1 and 0 3. Okay, so this is what we talked about. So a Jordan matrix is a block diagonal matrix whose diagonals are all Jordan blocks, right? So this I'll have here lambda 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 with algebraic multiplicity equal to 3, geometric multiplicity equal to 1. Okay, now if I have also say lambda is 2 2 2 with geometric multiplicity 1, and another lambda which is 3 with geometric multiplicity equal to 1, my block just populates in this way, and we can cook up several examples. This is how it will look always. Where does it come from? This comes from expressions like this. Okay, so this diagonal matrix is a special case of a Jordan matrix with each diagonal element forming a Jordan block. Okay, and then I can just write so this this will be my j. So A E is E j, or I think over there I just use the notation P, AP equal to PJ. So okay, just E and P, just notationally you can use whatever you want, and you just get a j which is P inverse AP. It's something like here, j is P inverse AP. Okay, so the lambda values are, again, these are sitting in the diagonal. Okay, and where does P come from? P has the generalized eigenvectors. So this is E1, E2, E3. Right, so this is what the P will comprise of. Okay, so you can try and find the Jordan form of this matrix. So this should be A equal to 2, 1, minus 1, 4. Lambda will be 3, comma 3. I'll have eigenvectors of the form. So A minus lambda I will look like minus 1, 1, minus 1, 0, sorry, minus 1, 1, x1, x2. So this will be equal to 0, will imply that any vector of the form 1, comma 1 is an eigenvector. Okay, so this is my, say, x1, and I am just abusing notations, but I am just looking at, okay, let me use x1, 1 and x1, 2 as the first and second coordinates of the vector x2. Okay, so can I find another vector? The answer is no, because there will be only this vector which satisfies this condition, any non-zero vector. Then I look at generalized eigenvectors. So I still have a, so this time I am looking for x21, x22. On the right hand side, this will be x1, which is 1, 1, resulting in x2 of 0, comma 1. And I just do this transformation P inverse AP. So my P, or what we called E earlier, will just be 1, 1, 0, 1. You do a inverse, you multiply this 2, 1, minus 1, 4, put a P here, 1, 1, 0, 1, you will get 3, 1, 0, 3. Simple, you can just check this out. Okay, now why are we doing all these things, and why is this useful for us from the state space point of view? So two matrices are said to be similar if there exists a non-singular matrix P such that this holds. Okay, so A we saw was similar to a diagonal matrix if it was diagonalizable, or A was also similar to a Jordan form if it is diagonalizable. Okay, so now what we know is that the eigenvalues of A and AZ are the same. Okay, I'll just say, I have lambda, A minus lambda I. I do the determinant of this, and on the right hand side I have AZ minus lambda I. Okay, so eigenvalues are same, which means the same characteristic equations should hold. So what is AZ? So this is P inverse A P minus lambda I. Okay, I can still write this as P inverse A P minus, I just left and right multiply this by P inverse AP, nothing changes, which means now I can do P inverse A minus lambda I and a P. P inverse and P go away, I'm left with A minus lambda I. So start with here, this gives me the same characteristic equation, and therefore eigenvalues of both A and AZ are the same. Okay, now what else can we do? Suppose I do some kind of a coordinate transformation. In the last lectures we had seen something about linearizing a system via coordinate transformation. So which means I just say I have x is P times z. So I just write down this as z equal to P inverse times x, because P is invertible Z dot is P inverse X dot. Okay, so what is X dot? I am just operating in the standard state space X dot equal to AX plus BU. So Z dot will be equal to P inverse X, P inverse AX plus BU. But what is X? I want to write everything in terms of the new coordinates, which is Z. So X is PZ. So I have P inverse A PZ plus P inverse B times U. So I have a similar matrix here, AZ, and some new B matrix. And we'll shortly see why these transformations are useful to us. Okay, so this I will get back to now a bit of control. So just to analyze state space formulations a little more. So we did a little bit of things earlier. So I had a state space realization. So given a transfer function Qs over Ps, I could convert it into a state space realization with A, B, C and D. X dot is, so the idea here is that one system can have infinite representations, right? So the system in X is similar to the system in Z because, well, all the properties, right? So the eigenvalues of P inverse AP are the same as eigenvalues of A. Instead of P, I take another Q and say I get the coordinates, say some W. They will still be the same. So any Q, any P, any R or any D or any infinite such matrices will be the same state space representation. Okay. So if I also maybe I'll just leave this a little bit as an exercise. So suppose okay, so what did we have? We have X dot is AX plus BU, Y equal to CX, and in the Z coordinates what did we have? We had Z dot is P inverse APZ plus P inverse BU, and Y equal to Cx. What was X? X was Pz. Okay. So Y will be CPZ. What is this? What is the transfer function? Transfer function is Y over U will be C Si minus A inverse B. I am leaving out the D term. Similarly here, Y over U will be, what is my new C here? This C, CP, Si minus A, this is my new A, I will just call this AZ, P inverse B. Simple computations will say that these are the same transfer functions. Nothing changes, right? So you can have infinite representations of the same system. So one of them is the say for example this very simplistically looking, this both will give me the same transfer function. Okay, so we started off with a differential equation of this form. I'll quickly go through this. So we called x1 as y, x2 as y dot, and so on, and obtain an equation which looked like this. So in the state space, I can write this as x1 dot is x2, and in a matrix of this form which only has entries on the last row, and u affects the last term xn dot, but you also through it affects the other term through these ones here. If y equal to x1, then I just have y is just 1 0 0 0 times the state. So this is my x dot is a times x, this is b times u, this is c, and this is x. Okay, nice. So now I'll go to the controllable canonical form. I think we also did this a little bit last time. We called, so let's say I have x1 equal to y, x2 equal to y dot, and so on. Differentiating each variable will give me x1 dot is x2 because it says y dot. Differentiate y dot, x2 dot is y double dot is x3 and so on. And the last equation I just solve for the nth order equation. So this just gives me an expression which is like this together with an output expression which is of this form. Again, we did this in one of our earlier state space motivating lectures. And what we also had this example about the mass spring damper system was very neatly by itself in the controllable canonical form. Similarly, I can write down an observer canonical form of which looks like this, where all the A's. So also simply we can look at this as the transpose of the A matrix, which is in the controllable canonical form, and this is the C transpose which was in the controllable canonical form, and this is the B transpose which was in the controllable canonical form. And this form we call it as the observable canonical form. We can write it in multiple ways. Both will mean the same, and whenever we need, we'll just see how to derive these expressions. So I can just write down the auto suspension system in terms of its observable canonical form. And if you look at what we had talked about in the DC motor, is through the voltage I am able to control the speed, right. So if I write in a controllable canonical form, so this is where my input enters. So what is here? Okay, okay, this is now the DC motor example. Because here the control input enters through the acceleration, but it also controls the velocity and therefore the position also. So in the DC motor, we could control the speed with the help of just regulating the voltage. The expressions, when I write it in a controllable canonical form, this will be a little easier to understand how we can control the system, right? So whether or not we can control the system, or is the system, so to speak, controllable. We'll define this shortly. Similarly, we saw that in the DC motor, what I can measure is the output speed. But with the output speed, can I just derive what the current is? Yes, the answer was yes, because we had expressions which related the current to so the speed to the current and so on. Okay, then we have the diagonal form. Okay, diagonal form. So I'm just doing it for a third order system. Let's say I have distinct poles. My state space realization will just have A matrix with P1, P2, P3 on the diagonal, B with all ones here, and C with some numbers, and maybe just looking at a D which is 0 here. Okay, so my A matrix is now diagonal. Okay, so I also know, given x dot equal to AX plus BU, how via E inverse AE this becomes a diagonal matrix just by computing the eigenvectors of A. Okay, so this is how it looks like. So what are the advantages of it? Computing E power AT and computing E power DT. So if I have, say, -1, 0, 0, -2, and I were to compute E power dt, this will simply be E power -t, E power -2t. Simple. Okay. So if I can convert my system into a diagonal form, will that be of any use? So I start with x dot equal to Ax. I ignore the B for a while, even though nothing, we lose no information because of that. The solution will be x of t is E power At x naught. And now say with the help of some coordinate transformation, how did we write that? Okay, just look at the slides. How did we denote the coordinate transformation? Was okay, x equal to p times z. Okay, so I have x equal to p times z, and in z I will have z dot equal to d times Z, where D is a diagonal matrix which comes as an inverse as P inverse AP, where P is just the set of eigenvectors of A. Okay, now what is Z of T? Z of T is e power dt times Z. How do I compute my original expression? So, if I go here and I relate Z and X, so X of T, this was equal to P times Z of T is e power dt times Z, and then okay, this X of T is e power at x naught. This is also equal to P times Z of T. What is Z of T? Z of T is e power dt Z of 0. So, I can write now my e power at as simply P e power d times t P inverse see, because what is x of 0? X of 0 is P times Z of 0. Okay, so I have e power at P times Z of 0 is P e power dt Z of 0. So, e power at I can write as P e power dt P inverse. Okay, so what has, so suppose I have a matrix 1, 4, minus 6 and 2. To compute e power at of this is not very straightforward, but if I change this to a diagonal matrix, so what I have is let us say lambda 1, lambda 2 are its eigenvalues. So, I just do e power lambda 1, e power lambda 2 with the t, I know what is P and I can also compute P inverse. So, computing the e power at becomes much easier when I am working with a diagonal matrix. So, many of the computations become simple. We also see how controllability analysis also becomes a little simpler. So, okay, some of these examples we can quickly work out and check that this a, b and c will give me the same transfer function. Similarly, with the Jordan form, I can still have Jordan blocks of this form as we saw earlier, and we can still have Jordan form, and then e power a t will be equal to P e power j t P inverse. Okay, so this will still hold, and now we can see how we can simplify our systems to give them some nice structural forms in terms of controllable canonical form, which will be used for controllability analysis, observer canonical form, which will be used for to estimate the states of the system, like can I estimate my current of the DC motor by just estimating the speed. Jordan form, diagonal form gives me nice way to compute my e power at, and also will be useful in controllability analysis. So, to summarize, we have just looked at different canonical forms and how we And what we'll see, of course, we saw how with a linear transformation we can get to a diagonal and Jordan form. We'll also see how starting from any state space system we can get to a controllable and observable canonical form. So using a linear transformation, I can go from one transformation to the other. And what we also saw was how the qualitative properties remained invariant under such transformations. So with this bit of math and different canonical forms, we'll go on to analyze some more properties of asking ourselves a question: is a system controllable, or when is a system controllable, and then build our analysis based on that. That's coming up in the next lectures. Thanks for listening.